For the next talk, I'll be pleased to welcome and introduce our second speaker, Dr. Tobias from the University of Paderborn. He works as a scientific advisor for FPGA acceleration at the Paderborn Center for Parallel Computing, and he will be presenting on the sparse matrix vector multiplication with hierarchical row reductions on FPGAs with high bandwidth memory. We also have Abdul Rahman Tareen, who did the practical work on this topic, and he will help answer the questions in the Q&A. Over to you, Tobias.
All right, thanks for the introduction. So you already said the important parts about Abdul having done the hard work of this, what I'm presenting. And also let me point out that we called our work HiHiSpMV for the hierarchical row reductions and the high bandwidth memory. And I know that you are all experts on the topic by now, but let me still start with the very beginning. So sparse matrix vector multiplication is an essential operation in linear algebra, for example, used in conjugate gradient methods. And we are essentially multiplying each row of the matrix with the corresponding vector entries to create one output value. And that means that every matrix value is used exactly only once, and it's clearly a bandwidth limited workload. The concrete arithmetic intensity depends on the sparse matrix format that is used. Popular formats are the coordinate list format, where we have 2 flops per combination of one value of the matrix and 2 indices, so both dimensions row and column index are stored. Or more efficiently, and the format that we are using in this work is a CSR format, where we have just one value and a little bit more than one index per non-zero entry in the matrix. So as a bandwidth limited workload, will it easily scale along the available bandwidth, just like the stream benchmark? Well, it's not that simple, for example, because the arithmetic intensity models also assume that we reuse the vector data all the time and only account for the matrix data in the bandwidth calculation. And that is not extremely trivial. So first of all, we need random access into the vector X, illustrated here. And secondly, we also have the problem that an previously unknown data-dependent number of partial results need to be accumulated into a single result entry. And a common pattern to implement this on FPGAs is to put the vector data all in fast on-chip memory, and then stream the matrix data from off-chip memories, so we can have a high bandwidth utilization. And one motivating work for our project was by Yain et al., which earlier on reached 97% bandwidth utilization on a single DDR memory bank. So that was also the time when the first FPGAs with high bandwidth memory started to show up. And so the idea was, okay, let's scale such a design up to the potential of high bandwidth memory cards, and we will get pretty good performance. Pretty good performance can be reached in 2 ways. So either we can use all the 32 HBM channels in 512-bit interface mode. In that case, we need a kernel clock of 225 megahertz to reach the nominal peak bandwidth of 460 gigabyte per second. Or we could use the same memory channels with just 256-bit interface, and in that case, 450 megahertz clock frequency is required to reach the same nominal bandwidth. Of course, nominal bandwidth is not what one will see in practice, maybe 90% of that, but it's still good to aim for a high nominal bandwidth, because these real-world differences show up for all designs, even if they are below this nominal bandwidth. And looking at previous work of SPMV on FPGAs with high bandwidth memory, concretely all using the Alveo U280 platform, which is, I think, still the most used HBM FPGA in the academic community. And we saw that The successor work by Yain et al. Focused on the 256-bit interface. They were able to use all the HBM channels, but couldn't reach the full clock frequency that is required to saturate the bandwidth in that case. So it works for a single kernel, but then scaling it to the full FPGA, clock frequencies always go down much below this 450 megahertz target. And then also we heard about Serpents already, which is able to use 24 of these memory channels in 512-bit mode. Clock frequency is easily reached. Here 24 channels are the channels used for the matrix data. 3 more channels are in practice used for the vector data. And there's also B8C, which also focused on the 256-bit interfaces and also fell short of the target frequency. It's still interesting though, because this work is using double precision arithmetic, so quite a number of variables regarding resource utilization and arithmetic intensity are different in that work. And finally, in this work, we will present an approach to reach 225 megahertz on the 512-bit memory interface, which almost gives us a nominal peak bandwidth, but it falls slightly short of this because the HBM clock doesn't come in at 450 megahertz, but at 434. So let's see what the further outline of the talk is. So I talked about the background and motivation of the talk and gave a first overview of how it fits together with related work. Now I will present the concept of hierarchical row reductions. Then I will go further to the full FPGA implementation with 16 compute units. And then we will look at concrete results. So let's start with the idea. So first step is to encode the matrix in CSR format. So that's completely standard. We take all the values, the non-zero values from the matrix, put them into the first list. Then directly in lockstep with that, we have a second list which contains all the column indices. So this entry comes from column 0, this entry from column 1, and this from column 4, which will also then point to the rows of the vector that we need to access. And then the compression comes by having not for every non-zero value a row entry, but rather we have for each row exactly one pointer into the 2 other lists to say where the next row starts. And in this example, this just saves us 2 entries. But as soon as we have, let's say, 20 entries per row, which is a very sparse matrix already, we already have just 1/20th of that storage in the pointer array. Now, how do we perform matrix vector multiplication on this? First step is pretty easy. We need to look up the corresponding factor from the vector for each of the entries. So we look by the concrete column index, pick the vector entry, multiply it with a value. And since this is all independent, we can do this in parallel. Here illustrated with a block size of 2, and our practical design then with a block size of 16. The only caveat is we have actually replicated the vector x, so we can be sure whatever index we find here, that we can in parallel access all these 16 entries and perform these blockwise products. Okay, and the next step will be, okay, we have all these partial products and need to accumulate these into row 1. This is easy, but then 4 of them into the row 4, I guess. And we do this in two steps. So first step, which we call L1, we accumulate entire blocks into one accumulated sum. And here there's a little trick, because if one of these intermediate block contains 2 different rows, partial results from 2 different rows, we do this in 2 cycles. So here we get one L1 result from the first block and another one for the row index 2. And then for these blocks, it's straightforward again. So just one partial result per meta block. And in the L2 step, then we need to perform accumulation on these intermediate results, for which we use the standard accumulation with shift register design pattern. Okay, so these are already the basic ideas. Finally, we need to write these intermediate results into the result vector. And with that, we can see the entire picture again. The operation is done. And this summarizes this view again. So the parallel multiplication into this blocks of products is straightforward. And this is a somewhat new trick that we applied in our design. So this was that much about the idea. Let's start looking at the concrete implementation. So we implemented everything with Vitis version 22.2 in this kernel. In this case, sorry, kernels come next. So we have for each compute unit 4 separate kernels. All of them are pipelined, most loops with an initiation interval of 1. And some of them contain additional data flow regions. And we process each block in 2 phases so that we can reuse the HBM channels. So the first kernel, the IO kernel, is connected to exactly 2 HBM channels. And in the loading phase, we first read the pointers and the vector X values. Store them in on-chip memory. And then in the streaming phase, we access the values and the columns through the same HBM channels and perform the operations I just talked about. So the first kernel there is then the multiply kernels. It produces this product stream, blocks of 16 partial products per clock cycle. The second kernel, this is easily unrolled since it's latency insensitive, as is the next kernel, which is then this L1 reduction, where we at most reduce 16 products from the same row, or if we have multiple rows, we do it in more than one cycle. So this is not in lockstep, but still unrolled and latency insensitive. And the last kernel, the accumulation, that one has this dependency. We always need to take the value from the new block and the last one and accumulate that. And for this, we employ the shift register design pattern with depths of 5 elements to accumulate these partial sums. So that much about the single compute unit. You can already see we have 2 HBM channels in use, and I talked about 32 HBM channels available. So overall, we need to scale this design to 16 compute units, and this is what we do with this approach. So we spatially tile the workload of the matrix in 2 dimensions. Each compute unit calculates the results of one exclusive part of the result vector. So this one is exclusive to the compute unit, and then the X vector is also split into chunks, and each compute unit independently cycles over all these tiles in the X dimension. So it's always this pattern: load the X vector and then process the matrix tile accordingly. And in order to have all compute units use almost equal amount of time, we have balanced the number of non-zero elements in the matrix per compute unit, and also the number of rows. To have the compute units calculate completely independent of each other, we have packed each tile into a continuous buffer in the HBM channels. So that looks like this. So we first have in this loading phase, we have the row pointers and the X values in the corresponding channels, and then we have the streaming phase where we access the columns and the values. We do this for all tiles, in this case 16. And finally, in the second of the used channels, the I/O kernel writes back the result vector. For this, we can set up a performance model that predicts the performance that we can expect for this design. We introduce an auxiliary variable d for the number of tiles in a compute unit. And then we get two performance numbers, one for the multiplication and one for the partial sum. Both of them have the same term in the beginning, which is a parallel term, number of non-zeros divided by 16 elements processed per block and by 16 compute units. And then both kernels have an overhead term. These are a little bit different. And depending on the matrix characteristics, it can be either the number of columns processed in the multiplication kernel or loaded actually in the multiplication kernel, or the number of rows that are completed in the reduction kernel. So this design we have implemented on the U280 card. We have 4 kernels. And we can look at the resource consumption. In particular, the DSP utilization can be perfectly explained. In particular, in the multiply kernel, we have 16 multiplications with 3 DSP each. I think there are 4 DSPs extra for address calculations. We have then the partial sum calculations where we reduce the blocks of 16. And finally, we have this accumulate kernel, which uses 5 shift registers with overall 1 + 4 × 3 DSPs. So this is the overhead that is needed to resolve the dependency on the result vector. But since it only occurs once per block and not for all these 16 calculations that we do in parallel, the overhead is quite small. Now looking at the concrete designs, we need to also provide the tile size, which in this case is 1875. So each tile can have up to this size in X and Y dimension. And in this case, then our BRAM utilization is 23 for the I/O kernel and the HBM interface. The multiply kernel uses 32 RAM blocks for the X vector, including replications. There are 9 BRAMs used for the pointer array and 8 for the accumulated results in the Y direction. URAMs are used only for stream FIFO buffers. So putting this together on the U280, we overall have a pretty low resource consumption, but the impression is not complete because this is just the kernel BRAM utilization. But when including the platform as instantiated in our case, almost all of the BRAMs are actually in use. So this is a critical resource. But critical resource would only allow us to scale up the tile size, but we already use all the HBM channels, so that goal is achieved. Now let's look at the physical implementation on the FPGA. So we have already seen the breakdown in kernels. Actually, this is not necessary. We also had a version where each compute unit consists only of one fused kernel, but in placement and routing, this version that I just presented is much more favorable. And then when we target the U280 with 3 SLRs, we need to distribute all the kernels to 3 SLRs. So we cannot put all the I/O kernels in SLR 0 and all other kernels in the other SLRs, because of the balance of resources used. So since each kernel has its individual balance, we need to distribute all the kernels to the chip. And in practice, we did this by assigning only the I/O kernels in round-robin fashion to the different SLRs. So we started in SLR 2 with compute unit 1. compute unit 2, compute unit 3, round robin going back up all the way, and then the final kernel was by random luck placed on SLR 0. And with this approach, we achieved the following goals. So overall balanced resource utilization per SLR. In particular, as discussed, the BRAMs are critical. We have overall an acceptable SLR crossing wire utilization. And with that, the kernel clock frequency of 225 megahertz was perfectly reached. The HBM clock fell just short of the target, so a few percent are missing here. Okay, so this is the design that we have then worked with and evaluated. Let's look at the test setup. So we have used the XRT native C++ API for the host code, and we have to use a legacy scheduler because the overall number of kernels doesn't work properly with the other scheduler variants. We have evaluated the design with 59 test matrices, ranging from around 3,000 to 25 million non-zero entries, and from dimensions n and m between 500 and 30,000, which is the upper limit of this design, this bitstream variant. And we have amortize the kernel invocation over 100 repetition, exactly the same evaluation method as done with Serpents. But I should add that our kernel launch overheads are a little bit higher, so it's more profitable for us to do this. In the long run, we should integrate everything with a CG solver where many kernel invocation, or where a single kernel invocation performs many SPMV operations. And with this, we can look at the results and compare them first to the performance model. So we have a prediction of the performance model here in terms of gigaflops, which we calculate by the number of non-zeros, 2 flops per non-zero, and divided by the time. And we see that generally the measured performance in blue follows the model, but we have some discrepancy. These are, first of all, caused by the actual kernel launch overheads, which are not included in the model, and secondly, by the difference between nominal bandwidth that we assume and the practical bandwidth that with the streaming interface can be achieved. Looking closer into some of the particularly well-performing matrices, we can also extract the measured bandwidth. So this is the total bandwidth for transferring metrics and vector data. And out of this, the vast majority is transferring metrics data. And with this, we can achieve close to 400 gigabyte per second bandwidth and almost 100 gigaflops in performance. Let's look at the differences between the peak performance of the best performing matrices and some of the matrices that perform not so well in more detail. So we have two factors at play that limit the performance. One is the matrix density. So from around 1% non-zeros in the matrix, we have some matrices which perform close to the peak performance. And once the matrix is too sparse, we have too much overhead transferring the vector data for each individual tile. And also looking at the overall number of non-zeros, we see that starting with around 1 million non-zeros, we get good performance in some matrices. And if it's lower, then the overall kernel launch times are a problem and show up in the measured performance. And since many of the practical matrices are correlated and have a low density and a low number of non-zeros, then these are the outliers which can be tracked here. We have also investigated the scaling characteristics of our accelerator. So far I talked about a design with 16 compute units. We did an experiment with fewer compute units. And for that, we scaled the tile size, or we scaled the supported tile size per compute unit such that overall it's always possible to execute matrices with 30,000 dimensions, 30,000 in both directions. All the designs are running at the same clock frequency, even though the smaller designs could run faster, but for a perfect comparison, we fixed it to this. And we see for some matrices, so this is a logarithmic scale, and we doubled the number of compute units between the experiments. And here we see with even distances between the lines, that is perfect scaling. And we have two interesting observations. So there are some matrices which perform perfectly well with a single compute unit, but where we have a scaling problem that limits the overall performance at 16 compute units. But there are also matrices where even the single compute unit is not well saturated, and then scaling drops even further. Now let's compare these results to related work. So we have compared all our results with Serpents. Since it's open source and the bitstream was available, we have been able to rerun all the experiments on our system. And then for the two other related works, which one we called LEAM and the other B8C, we only picked the results that they explicitly mentioned with metrics name in the paper. And these results here show the combined effect of peak bandwidth, which is always higher in our design, or which is higher by design, and the actual bandwidth utilization. Which is interesting because we see, for example, that in some matrices, Serpents performs much worse than our design, and in others, for example here, where our design doesn't have a very good bandwidth utilization, then Serpents performs better. But overall, in the big picture, HiHiSpMV performs pretty well. Let's quickly look at another perspective, why the other designs might not have been able to reach this high peak bandwidth or nominal bandwidth. It might be related to resource consumption, but it's not a very clear picture. So for Serpents, we only have the resource utilization numbers for the A16, so 16 HBM channels design. But still, it overall might be more resource efficient. The others seem to be using more flip-flops or maybe more lookup tables, which might explain their scaling limits, but it's not a one-to-one explanation. So with that, let's go back to the big picture and a summary. So the first goal of obtaining nominal peak bandwidth on the U280 platform was almost reached. For that, we settled on the 512-bit interface and the 225 megahertz interface because we believe it's hard to achieve 450 megahertz for a large design that can utilize all the memory channels. And I have talked about some of the features that allowed us to scale the design up to that level. And then the other important feature is bandwidth utilization, where the picture is not that clear. We have focused on CSR variant versus COO matrix format in the other cases. But this also leaves more headroom to explore in terms of index compression, how many bits are actually needed for the row and column indices. We have presented a new idea performing or accumulating the results in a single row per cycle versus other designs that try to resolve accumulation conflicts in different ways. We have this limitation to a single row per cycle that may be solvable, but at increased resource cost, which then will impact the total performance again. And we also have trade-offs in our approach using vector replication, which limits the blocks size, which then has a negative performance impact on particularly sparse matrices. And in future work, we want to look at integration with a conjugate gradient solver as well and look into multi-FPGA scaling. Let me quickly point out the references I mentioned throughout this presentation. Our work was presented at FCCM this year. This was a single DDR channel design, and these were the three best performing SPMV designs on U280 so far. And on my final slide, let me point out that at the Paderborn Center for Parallel Computing, as a HACC center, we are operating 48 Alveo U280 cards, plus in smaller quantities other accelerators. And academic researchers with interest in FPGA acceleration in HPC can apply for compute resources within the HACC program and beyond that through this link. It's all the same link. And also the source code and bitstream of HiHiSpMV are available if you want to reproduce results or try to improve upon this. And with this, I'm done. Thank you for your attention, and I'm happy to take questions if there are any.
Thank you, Tobias. So we're a little bit over time. So if you have any questions, feel free to put them in the chat. I have just a couple of comments. So I'd like to invite everyone to the next HACC Talk on 22nd August, where my AMD colleagues, Tom Papatheodore and Giacomo Capodaglio, will present on the topics ROCm ecosystem and HIP programming and profiling tools for AMD hardware. And thank you again to both the speakers for the two great talks, and to everyone who joined, and particularly to those who asked questions. And again, if you have more questions, feel free to connect with the speakers on the HACC user community. A reminder that you're welcome to apply to join our HACC program to get access to high-end heterogeneous computing hardware and engage with the community there. You can find the details on the webpage shown on the screen.